dealing with transformations, dealing with horizontal and vertical transformations. Horizontal shifts occur inside the parentheses. We're doing this C value. And it's always the opposite because this is what we did in chapter 1, the equations of circles. So it's always the opposite. So what's this graph going to look like? The first thing you always have to do is tell me the original function. What is the basic function from the library of functions here? Nope. There's not one x equal x minus 3 in the library of function sheet. Look at the library of function sheet we did last weekend. You won't find it in there. That's the stuff you had to do in class when we did transformations. I mean, we did the first before we started this chapter. So what's the basic function look like? Didn't we do library functions? Answer, yes. It's in your notes somewhere. Nobody's flipping through their notes. Some of you all just falling asleep. The basic function here is x squared. I'll get your notes out anyway. I mean, that's the first thing you should do when you come to class instead of playing with your cell phones is get your notes out. Review your notes you did last time. That's what you should do as students. What does the x squared look like? The graph. Did you find it in your notes anywhere? Why? I mean, then pretty much if you guys don't know the basic functions or even look at your notes, why am I even lecturing today? Why are you even? I mean, so the basic function is x squared. It's a parabola. Inside the function, what does it do? Now we look at, are there any horizontal shifts? Inside the parenthesis, we have an x minus 3. What that means, if I set it equal to 0, I get x equals 3. That means my origin shifts 3 spaces to the right. So there's my new origin. I shifted from here to there. So my graph looks the same, but shifted to the right. It's a horizontal shift 3 to the right. What does that graph look like? Oh, it's not even near funny. The function here is square root of x. What does the square root of x look like? You didn't fill it out. We gave it to you. You didn't fill it out. We did it in class on paper. You were supposed to transport it to that. So what'd you get? What's the graph look like? Very good. It starts at origin and goes like this. So that's the basic function. Now, is there anything inside there? Yes, there's a horizontal shift. We know it's -2. So it moves, my new origin is at this location. 1, 2. So there's my new origin. The graph looks the same. Those are horizontal shifts. They happen inside the function. All horizontal changes occur inside the function. Usually in parentheses. Now, what does that statement mean? Okay, you have to know what the functions are. Since this function is a square root, inside the function is where the x is. It's inside the function. That's all horizontal changes. In this case, since it's plus or minus, it's a horizontal shift. Let's look at vertical shifts now. The vertical shift happens with the d value. A, the function bx minus c plus d. This one here. All vertical changes occur outside of the function. For this one, if the value of d is positive, you shift the entire graph up d units. If d is negative, shift down d units. Graph both of these. So in the first one, what's the basic function? It's the absolute value of x. What does that look like? What's that? AV, very good. So what is it? Is there a horizontal shift? No, because nothing's happening inside the absolute values. So is there a vertical shift? So horizontal shift, none. Vertical shift. What does that tell me to do? It even says right here, if it's negative, it shifts down 3 units. This is -3. One, two, three. So there's my new origin right there. So the V, the graph looks the same since nothing changes. It just changes location. It'd be easier if you sat at the end of the table rows instead of the corner. Hey, all of you, I mean, it's easier to see the board if you sit on the inside instead of next to the wall. How about this one? What's the basic function here? Are you asking me or telling me? What does that look like? With your pen in the air, do it. Very good. Very good. Very good. Is there a horizontal shift? Why not? There's nothing, yeah, there's no parentheses, nothing inside there. Nothing, in other words, nothing is added or subtracted to C before you do the cube. So there's none. Is there a vertical shift? Up to, because it's positive, it's outside the function. See, the function is right here. Anything outside of it is a vertical shift. So far, so good? All right. The third transformation, oh, let's look at example 1. Sketch these graphs. Let's look at these 4 graphs. Okay, the first one. What's the basic function? What does that look like? Very good. Parabola. Is there a horizontal shift?
No.
No. Is there a vertical shift? Where? Very good. -6. So the graph 1, 2, 3, 4, 5, 6. It still looks like that. At least for the homework, you still have to plot some points. All this is, I'm rough sketching it. All right, you know where it is, so you plot some points. +1, -1. How about B? What's the basic function there? It's the absolute value, which is a V. Is there a horizontal shift? How many spaces where? Why is it to the right? Because it's positive 4. It's opposite what's inside there. 1, 2, 3, 4. So there's my new origin. So there's my graph. All right, C. What's the basic function of C? Pretty much, it's easy to find the basic function. Anything that's plus, minus, just erase all the numbers, except that 3, because it's part of the function. Cube root of x, because that's a cube. What does a cube root look like? Yeah, like the one going up. Yeah, like this one, but going this way. Exactly, it's going this way. Is this one an odd or an even function? Is this function odd or even? Why? Anybody help? I didn't put it on that sheet, the graph sheet. We talked about it last week with symmetry. We know it's odd. Well, first off, because there's a 3 there. That's odd. Because to be odd, you have to be symmetric about the origin. So this point matches that point. If you change x, the signs. If you change the signs of this point, you get the other point on that side. How do you know if it's even? I mean, if you're going to listen to your earbuds while you're in class, then don't even show up. What's that? Yes, it's symmetric about the y-axis. So in other words, x squared is symmetric about the y. It's an even function. So is the absolute value of x. This point and this point share the same y. Now let's put it together. Let's look at this one. What's that one going to look like? So the basic function here. Actually, let's make it. Yeah, let's do that. If you take away all the numbers, what do you have left? Square root of x. That graph is different than x squared. What does that graph look like? Nope. Right. It starts from there and it goes that way. See, it's a lot easier if you. It's only 12 graphs to memorize. You know some of them already: linear, constant, quadratic, the square, the u one squared. Memorize those. It'll make life much easier for you. What's the horizontal shift, or is there one? Asking me or telling me? Anybody agree? Yep, because it's inside the function. The function is square root of x. Is there anything plus or minus the x inside there? Yes. So there's a horizontal shift to the left 2 because it goes to -2. 1, 2. So there's our new origin there. So it shifts that way. Is there a vertical shift? Where, how many? Yeah. Because remember, inside it's opposite, outside it is what it is. So what that one says is now I go down 3 spaces. 1, 2, 3. So my new origin is right here. I shift left, down 3, and my graph looks the same. That's all a transformation does, is it changes the location of the origin. So far, so good? You want to copy these down while we do the next one? We're starting the third one. The third transformation. Because we did horizontal, which is inside the function. Vertical is outside the function. But there's something else with respect to those. We have what are called reflections. What's a reflection? Exactly. Exactly how you say it. Mirror image. We've actually talked about this a little bit last week. So as reflections, we can have one about the y-axis. For example, the u squared, the x squared. If x is 2, what's y? If x is 2, what's y? Hmm? Where are y'all looking? Is there an equation or a function in there anywhere? Let me give you a little hint. No, that's an equation. There's an equal sign. This equation is that graph. When x is 2, what's y? Right, because if x is 2, 2 squared is 4. Which means that if I change the sign of this number and plug it in there, what do I get? If I get -2 and put it in there, what do I get? Let's try it. -2 squared means -2 times -2, which is what? +4, which is the same thing there. That is a reflection about the y-axis. So what defines a reflection about the y-axis? Here's the formal definition. If I have a function and I plug it in there, I get some value y. If I take that same function and put the negative of that input, I still get y. And that's what I did here. I put 2 inside there, I got 4. I put -2 in there, I got 4. That means it's symmetrical about the y-axis. So in words, what does this mean? if I change the sign of my X value, of the X value, I get the same Y value or solution. All right, so that's about the Y-axis. And that's how you would test it. I give you an equation, plug a number in there, and plug the same, let's say put 7 in there. You put -7, just change the sign of what you're putting in there and see if you get the same answer. If it does that, then it's even. I mean, then it's about the Y-axis. And that's what we call an even function. An even function. If it's symmetric about the Y-axis. And there's a shortcut to determine whether it's even, odd, or neither. I'll show you about that in a second. If it's symmetric as a reflection about the X-axis. In other words, if I had a point here at some value X and some value Y, it's symmetric about the X-axis, then I'll have another point down here, but at -Y. So this is at point XY, this is at point X -Y. So you see, the only thing that changes is the sign of Y. It remains the same number, but has different signs. And the X stays the same. So what this says is this. So it's easy to follow. Now let's put it this way. In other words, if I put in a value of X, I get 2 values of Y. This is called a hyperbola. As opposed to a parabola or parabola. You notice how bola is at the end of both of those. Parabola goes up, hyperbola goes to a side, depending on what the values of X and Y are. So here, the sign of Y of the Y value changes for any X value. So if I have X, I get Y, and I plug it in, I get -Y. So it's 2 values. Is it a function? – 50-50. It's not a function because it fails the vertical line test. Remember, a function cannot cross the graph more than once. Then you can ask, okay, do we know a graph like this? Yes. We actually use that function. If you think about it, the graph looks like this. But where did this equation come from? Later on, we'll learn to get rid of a square root. What do I do? Good thought to know. If I square both sides, the square and the square root cancel. This function looks like that, or that equation looks like this, and this equation looks like that. Why do we not put the whole thing there? Because it's not a function. So there's a rule in mathematics, a property that says if your function is undefined at a certain point x, you can make it a function by redefining the domain. Here, or if you do that, then you affect the range also. I only want the positive answers. So that's what that looks like. And let me give you a hint here. Here, if you're given an equation that has an exponent, that exponent is called the degree. We'll talk about this more later on, but this is going to help us. For example, here you have x squared. The degree tells us the number of solutions possible. So you're asking, okay, now, this one's, you said that there's two possible. What does possible solutions means? Well, if you draw the graph, a solution is solution, the x-intercepts. So whenever we say solutions, we're actually talking about the x-intercept, where it crosses the x-axis. There's two of them in this case. Or we can have one solution right there. Or we can have no solutions, because it doesn't cross the x-axis. That's why I say the number of solutions possible, possible solutions. That also helps us later on when we start solving these things. Whatever the highest exponent is, there's two solutions. Because this one's on the y, that means here's one solution, here are two solutions, there's no solutions, because it doesn't cross the y-axis anywhere on that one. Yeah, we'll go more into depth later on. So that's about the x-axis. The third one is about the origin. This one's about the origin. What this one looks like is if I put a positive x, I get a value of y. If I put the same value but opposite sign, then I get the same answer but opposite sign. So this one basically if the sign of the X value changes, then the sign of the Y value changes. That's how you can tell if it's symmetric about the origin. So here's a point. Here's my X and Y value. But if I put the negative X in there, then I get the same value of Y, but this time it's negative. If it's symmetric about the origin, it's an odd function. Again, the way you test it, plug it. If I give you a function, plug a value X, I don't care, it could be a 2. Then plug it in -2 and see if it's the same, if you get the same number, but different signs. Then it's an odd function. It's symmetric about the origin. Do we know any functions in our library that are odd functions? There are 3 of them off, 4 of them that are odd functions. Yep. One of them is this one. What function is that? Y equals what? X to the power 3. Very good. Do we have another one? Do we have another function? Because the reason this one's odd is because whatever X I put in there, I get a value of Y. If I put a negative X, then I get the same value, -Y. What's that? Very good. The linear equation. What does that equation look like? Y equals X. Because if X is 3, Y is 3. If X is -3, Y is -3. So it's symmetric about the origin. It's an odd function. What else? What's the power of this one? What's the degree of this one? If there's nothing there, what number's up there? 1. Another one. Which one? This way? It's no, actually, good question. The question was, is it any different if it's like this? No, because if I put an X value, I get a Y value. It'll give me the same value here, but the signs change. That's all you want is the signs to change. It'll be the same values, same numbers, but different signs. That's how you can tell it's symmetric with the origin. We just did one up here. What is that graph? What function is that? Very good. The cube root of x. And the last one, like that. What's that function? What's the equation look like? Very good. Yes, it's irrational. Why is this one an odd function? What's the exponent of x? What's the power? 1. You notice how all these exponents, all these numbers are odd? That's why it's an odd function. The same logic goes for even functions. All the graphs that are even have a power 2 or are constant. Let's go back to the other side. Let's look at all the even functions. So what's the first one that we know? Yeah. The parabola. What's that function? Yep. What's another one? That's symmetric about the y-axis. It's not a function because you can't draw a vertical. Oh, yeah. Maybe 5 of them. The absolute value of x. Very good. What's another one? The square root of x, but it's only on one side. It's not symmetrical at the other side. So no. Good try though. No. There are actually 3 more. Yes. What does that graph look like? That's that. But what does the graph look like? Like the Atari symbol. What's another one? Not a function. Has to be a function. What does that graph? What does that function look like? It's a constant function. So if this value is at 2, then it's y equals 2. Is there another one? The greatest integer function, that one would be symmetric about the origin. There are only 5 left. It's not the greatest integer function, so it's only 4. It's not square root. We talked about that. It's not square root. It's not the cube. It's not the cube root. It's not 1 over x. It's not the x. Yeah. I may have been thinking that, not that one, but these are the basic ones. All right, let's look at. Now let's look at stretching. What does stretching mean? We have 2 types of stretching. We have horizontal stretching, pulling it apart, or we have horizontal constriction, this is stretching, this is constriction. That's horizontal. And then vertical stretching would be pulling it away from the origin as opposed to squeezing it. This is the stretch. This is the constriction. So we can make it wider, we make it narrower, you can make it taller or shorter. This one is dependent on, has to happen inside the function. So which variable would be our horizontal shift? Our horizontal stretch or constriction? What did C do for us? What does the C value do for us? Horizontal shift. What does D do for us? So we have A and B now. Ooh, hold it. I should have done reflections with A and B also. Okay, before we start in these, what if A and B are just signs? Right now, they're what? They're positive. What happens if they become negative? What happens when A and B change signs? In other words, we're A and B, and they change signs. So if A changes sign, again, it's outside the function. So what happens? What direction does that one go? Horizontally or vertically? Right. Very good. Any changes inside are horizontal, any changes outside are vertical. If A changes sign, the graph flips about the horizontal axis. If A changes sign, the graph flips about the horizontal axis. Here is an example. What's the function? What's the basic function? Think of order of operations. Is multiplication or exponent more important? You're asking me again. Right. Because special operations are done first. So the graph of this one, the function of this one is x squared, and it's that u function. Horizontal shift, none. Vertical shift, none. Is there a reflection? Yeah. So now what happens is no matter what x's I have, they now become negative. So it flips about the x-axis. So basic function here is what? Squared. X cubed, I mean, because there's a power. Remember, get rid of all the numbers. Where's the x? There. There's the power, so it's x cubed. What does the graph look like for x cubed? It goes up. It's an increasing function, right? Is there a horizontal shift? Where? Yeah. Two to the right. So it's 1, 2. So there's my new origin. It's still an increasing function. Is there a vertical shift? No, there's nothing plus or minus behind it. Is there a reflection? Yeah, that one there. So what we do there, remember that's at 2. Our graph used to be like this, but I got rotated about the x-axis. So now it looks like this. This part goes down, this part goes up. It's now a decreasing function, which is negative. And we do something, if we had a vertical shift, we'd shift it that way too. All right, so that's what happens when the leading coefficient changes signs. Now let's look at B. If B changes sign, then we rotate about the y-axis. What's the basic function of this one? I don't see an x squared in there. There's a square root. What's the graph look like? We've done enough of these. You guys should just know it by your top of your heart, your mind. Is there a horizontal shift? Is there anything added or subtracted to x inside the radical? None. Is there a vertical shift? No, because there's nothing plus or minus behind it. Is there a reflection? Yeah, since the value of x changes signs, now it's supposed to be positive, but now it's negative. It happens inside, so it's a horizontal flip. We flip across the y-axis. So if x is negative, you draw the graph and then flip it across the y-axis, the horizontal, the vertical axis. I should say, then rotate about the vertical axis. Because you won't always be at the origin. When we do horizontal and vertical transformations, we're no longer at the origin. You're still flipping your horizontal across the vertical axis. All right, so that's if A and B changes signs. What if A and B change values? Horizontal transformation. Remember, where does everything horizontal occur? Inside or outside the function? So here it's either going to be a horizontal shift, shrink, or stretch. And remember, so this is the B value. And remember, everything that happens inside the function is always opposite. So if the value of B, or I should say the absolute value of B, is greater than 1, then divide the x value by B. Because now these transformations, or the shifts, the shrinks and stretches, don't change locations. We're now changing where the points are. In other words, What's happening here is this. So this is absolute value of x squared. What if I had 3x squared? If the absolute value of b is greater than 1, then we multiply. Well, we have here, if this is true, then we have a horizontal constriction. We're squeezing it. It's a horizontal squeeze. In other words, it's going to be skinnier. Let's see this. Let's look at 2 points here, 1 and 2. When x is 1 right here, what's y? When x is 1, 1 squared is 1. When x is 2, what do I get? Now let's look at this one. When x is 1, what's y? Well, 1 times 3 is 3. 3 squared is. So now it's 9. It used to be 1. Now it's 9. Now it's all the way up here. It's much skinnier. And that 2 times 3 is 6. 6 is 36. So you see how skinny it gets. It's compressed because this number is positive. I mean, it's bigger than 1. If my absolute value of b is between 0 and 1, multiply the x value by b. And what that's going to do, that's now going to change our horizontal, is going to stretch it out. Let's see this one. Y equals x squared. Y equals 1/2 x squared. It's inside the function. So on our original one, when x is 1, y is 1. When x is 2, y is 4. And the same with the negative. So what happens here? When x is 1, we have 1 in there. Now, 1 times 1/2 is 1/2. 1/2 squared is 1/4. So this one becomes 1/4. When x is 2, 2 divided by 2 is 1. 1 squared is 1. So you see, now it's going to grow a lot slower. It's pulling apart. It's stretching it. So if the b value is between 0 and 1, it gets wider. if absolute value is greater than 1, it gets shrunken, or I don't want to say this, compressed. The graph, the walls come in, the walls go out. So that's B. Remember, it's going to be opposite. So if it's a fraction, it'll get wider. If it's a big number, it'll get smaller. So that's inside the function. Now for the A value, remember, anything that happens outside of the function is a vertical transformation. A vertical transformation. In other words, if the absolute value of A is bigger than 1, the graph gets taller. If the absolute value of A is between 0 and 1, the graph gets shorter. Basically, here, if it's greater than 1, you multiply A to the Y value. And if it's a fraction, you divide the Y value by A. So again, anything that happens outside, it is what it is. If A is big, if the coefficient is big, it gets bigger. If it's small, it gets smaller. Unlike the X value inside there, if A is big, it gets narrower. If it's fraction, it gets wider. It's just the opposite. Let's look at both of these. So what's the original function in that one? X squared. When X is 1, Y is 1. When X is negative 1, Y is 1. When X is 2, Y is 4. And when X is negative 2, Y is 4. That's the original one. Now what do I do? So at 1 and 4. Here, I do that first. I square it. Then what do I do with my A value? I multiply it by 3. So in this first one, when X is 1, I get 1. Times 3, I get 3. When X is 2, 2 squared is 4. 4 times 2 is 3. 12. So it goes all the way up to 12. So it gets taller. It stretches it. It looks like the compression, doesn't it? basically has the same result. This one, when x is 1, y is 1. When x is 4, y is 2. When x is 9, y is 3. That's why this one looks this way. That's the square root of x graph. But now, what does this tell me to do with each of my y values? Multiply by 2. So at 1, it's now going to equal 2. When x is 4, square root of 4 is 2. 2 times 2 is 4. It's not going to be up there. So it's going to grow like this. So again, it stretches vertically. And just do the opposite. If it's a fraction, this one would be 1/2 square root of x. This is 2 square root. So you see what happens if we have an integer in front of it, it gets bigger. If we have a fraction, it gets shrunken. Let's put this all together so we see really how to do it. If I give you a graph, the graph I'm going to use what we had in our example here. I'm going to give you this one. So draw that graph on your paper real quick, because we're going to use that to reference. So we have -5, 0. There's a point. -2, 4. 0, 0. 1, 2, 3, 4, 5, 6, 7, 8. Then we have another one at 4, 0. All right. This is our function f of x. We're going to do these changes to it. Two times f of x. 1/2 times f of x. F of 2x. F of 1/2 x, or f of x over 2. We're going to do all those transformations. So look at A. We're going to now graph A. We're going to use this graph, and we're going to graph A. So what does this tell us to do? What values in my graph, what values change? Is this going to be a horizontal or vertical transformation? Why? It's that side. So since it's vertical, all we do here, all of our y values, multiply them by 2. Take all of the y values and multiply them by 2. So does this point change? No. So it stays at 5, 0. Does this point change? To what? Negative 2, 8. So now we're all the way up at 8. The origin doesn't change. What happens to this one? To where? Very good. So at 2, it goes all the way down to negative 16. And then the other one doesn't change. So yeah, we're stretching it vertically. What does this one do? Shrink it. So here, since it's outside, we take all of the y values and divide by 2. Yep. So yeah, so this one here, take the y value, 4 divided by 2 is 2. Negative 8 divided by 2 is negative 4. So it becomes a lot smaller. So if it's outside, it's a vertical, up and down. If it's big, it stretches it. If it's short, if it's small, it makes it shorter. What does this one do? Remember, inside it's opposite. So here we take all of our x values and divide them by 2. So let's see, here's C. So this first point becomes what? Take 5, negative 5, divided by 2. So what is negative 5 divided by 2? Negative 5 divided by 2 is negative 2 and 1/2. So it becomes there. Negative 2 and 1/2. What happens to this point? Yeah, now we take negative 2 divided by 2. So we get negative 1 to 4. So that looks like this. This one doesn't change, so it stays at the origin. What happens to this point? Right, divide the x value by 2, which gives us 1, and it's going to be negative 8. It's in there. And this one becomes 2. So you see, we used to be all the way at negative 5 and 4. Now, because of this change inside there, we shrunk it. It squished in. What does this one do? It multiplies by 2. Why is it very good? Why do we multiply by 2? And so we flip it and multiply to the x, right? Because if we put negative 5 inside there, so negative 5 divided by 1/2 becomes negative 5 over 1 times 2 over 1 makes it negative 10. So this one now goes all the way out here to negative 10. -2 becomes what? Remember, we have 1/2. So we multiply by 2. So -2 times 2 becomes -4. So it looks like this. And the 0 stays there. This 2 becomes, yeah, because we're only doing inside the x values. So because it's 1/2, we multiply by the reciprocal. So it becomes 4. So the graph looks like this. And this one goes all the way out to, this one goes all the way out to 8. So if it's a fraction inside there, it stretches it out. What happens in this last one? This is the same as this one. So we know it's going to be y. What does that negative do inside there? Reflected about where? Yes. So in other words, we take the graph and flip it this way. Yeah, so it's going to be all the way to -8 to 0. So -4, we have -8. Then at +4, we have 4. And then at +10. So we have this graph. Just take the graph and flip it over across the y-axis. It's not difficult, but it takes practice because it's very easy to get confused. And that's why I gave you this last page here. This last page pretty much tells you what to do. Woo! That section was painful.